Now we move to section B. This is January 2026, Unit 2. We move to section number B. Section number B, we move to question number 17B. It says complete the table for the values of butane by using your graph, and you must show your working. Now you need to plot this graph. I haven't plotted the graph, I've just sketched. I've just made a sketch here. It's a rough sketch. So what you need to do is you need to complete the table from the values in the graph. Now if you look at the table, you have to find the enthalpy change of combustion in gram per kilojoule. How do you find this? You can find this from the number of carbon atoms. It says it's butane. Butane has 4 carbon atoms. So you go to the plot, you go to number of carbon atoms, 4 carbon atoms, and its corresponding enthalpy change. According to the marking scheme, since I haven't plotted yet, according to the marking scheme, this should be minus 49.4. This should be minus 49.4, something like that, yeah. Should be minus 49.4. So the enthalpy change here would be minus 49.4 kilojoules per gram. Now you have to calculate the enthalpy change of combustion in kilojoules per mole. So this was per gram and this is per mole, right? So when you burn 1 gram, so you can find this using the unitary method. So when you burn 1 gram of butane produces 49.4 kilojoules, right? So therefore 58 grams of butane will produce, because 58 is the molar mass of butane, right? So if you calculate the molar mass of butane, molar mass of butane is 12 multiplied by 4 plus 10 is 58. So 58 grams of butane produces 49.4 multiplied by 58. 49.4 multiplied by 58 will be 2865.2. So this would be equals to minus 2865.2 kilojoules per mole, right? So this would be the answer. So you copy this answer and we put this here. This would be the answer. Okay, then we move on to the next question. The next question is question number C. Question number 70C says a graph of enthalpy change of combustion against the number of carbon atoms is approximately a straight line from ethane to hexane. Okay. From ethane to hexane, it's a straight line. The enthalpy change of combustion is a straight line. Explain this statement by considering the bonds broken and made in the combustion of alkenes. You have to explain this statement by considering the bonds broken and made in the combustion of alkene. Okay. Now if you look here, for example, if you have ethane, C2H6, and if you have propane, it is C3H8, right? So if you compare the two molecules, as you go down the homologous series, it increases by CH2, right? When you move from ethane to propane, it increases by CH2, right? It increases by CH2. Now if you carry out complete combustion of C2H6, it will produce 2 moles of carbon dioxide, produce 3 moles of water, right? If you carry out complete combustion of propane, it will produce 3 moles of carbon dioxide and 4 moles of water, right? See, basically what happens when you move from C2H6 to C3H8, the formula increases by CH2, right? Each formula increases by CH2. See, the next member is C4H10, so it also increases by CH2. So if you carry out combustion of CH2, CH2 would form, see, CH2 would form one carbon dioxide and one water, right? If you carry out combustion of CH2, CH2 would form one carbon dioxide and one water, right? So what's happening? See, from 2 CO2 is becoming 3 CO2 because the carbon number increased, because the carbon number increased by 1. So there's one more carbon dioxide here, right? Because previously it was 2 CO2, now it's 3 CO2. So there's 2 hydrogen. If you carry out combustion of 2 hydrogen, it will produce 1 mole of water. So the number of water molecules also increased by 1. Get the point? Every time there is an increase in number of carbon atom, the number of moles of carbon dioxide formed increases by 1 unit. And the number of moles of water formed also gets increases by 1 unit. So when you are moving from carbon number 2 to carbon number 3, there is an increase in 1 carbon dioxide and 1 water. If you move to carbon number 4, there will also be an increase in 1 carbon dioxide and 1 water. If you move to carbon number 5, there will also be an increase in 1 carbon dioxide and 1 water, right? So every time the number of bonds being broken and being made are the same, right? So since it gets increases by CH2, so the number of bonds broken, so as we move from, let me write the answer for you. As we move from ethane to hexane, one more carbon-carbon bond and 2 carbon-hydrogen bonds and 2 more carbon-hydrogen bonds are broken. And since it produces, 1 more carbon dioxide and 2 more carbon-oxygen bonds and 2 more OH bonds are made. Sorry, not broken. These are made. So every time there is an increasing number of carbon atoms, exactly the same things go on. As you move from ethane to propane, this happens. As you move from propane to butane, again this happens. As you move from butane to pentane, again this happens. So the increase in the enthalpy change is always the same. All right? Then we move to question number 18a. Explain why bromine has a lower electronegativity than chlorine. Now, bromine has a lower electronegativity than chlorine because bromine has greater shielding. Because bromine has greater shielding. Or you can also write that bromine has a larger radius. So it has lesser attraction for bonding electrons. Oh, since we are comparing this with chlorine, we have to write it has a larger radius or greater shielding than chlorine. You have to write that because we are also comparing it with selenium. So you have to write that. So it has a lesser attraction for the bonding electrons of the bonding pair. Okay. Then you have to compare about bromine and selenium. So bromine has more protons than selenium. So it has a greater attraction for the bonding electrons. So you get 1 mark for this point, 1 mark for this point, and the third mark is for is writing about attraction. The third mark is for these 2 points, about greater attraction and for lesser attraction. For these points, about saying bromine having lesser attraction and bromine having greater attraction here. For these 2 points, you get 1 mark, and for this point and this point, you get 2 marks. So total you get 3 marks. Then we move to question number B1. B1, it says observation with silver nitrate. With silver nitrate, the bromide ion will give you a cream colored precipitate. So we write cream, or you also write pale yellow precipitate. You can't write yellow, you can write pale yellow. You can write off-white. Yellow will always be rejected. You can write pale yellow. Or you can write off-white. All of these are correct. You can't write yellow. Yellow is wrong. Okay. Then you have to write the ionic equation. Ionic equation for this reaction would be Ag plus aqueous plus bromide aqueous ions produces solid silver bromide. Because this appears as a precipitate, state symbol should be a solid. Observation with concentrated ammonia. If you add concentrated ammonia, this silver bromide would dissolve. This silver bromide would dissolve and the precipitate would dissolve. So you can write precipitate dissolves and forms a colorless solution. Because silver bromide is completely soluble in concentrated ammonia. Concentrated sulfuric acid is added to solid potassium bromide. You have to explain 2 observations. One observation is that this will produce steamy fumes or misty fumes of hydrogen bromide. You write misty fumes. This can be one answer, or steamy fumes. Then this reaction also produces bromine vapor. So you can write brown vapor, or you can write brown gas, right? So these are the 2 observations that you can write. These are the 2 prominent observations. There might be more observations. You can consult the mark scheme as well. Chlorine gas is bubbled through a dilute solution containing aqueous bromide ions. So if you react chlorine gas with aqueous bromide ions, this reaction would produce 2 moles of chloride ions and 1 mole of bromine aqueous. Yeah. Oh, sorry. That's the equation. Sorry, I'm supposed to write the observation. Oh, the observation is pretty easy because the reaction produces bromine. The reaction produces aqueous bromine. The color of aqueous bromine is orange. So the observation would be that the solution turns, that the colorless solution turns orange. Observation is solution turns orange. Or you can also write yellow because bromine water also looks yellow. Right? Now we move to question number C. Question number C is an interesting question. Question number C says, this mole of chlorine gas was passed through an aqueous solution containing both potassium bromide and potassium iodide. Calculate the number of moles of bromine and the number of moles of iodine produced assuming all the chlorine has reacted. This question, I think, a few years back, this question was in the exam. Similar question, exactly similar question. It's a very good question and very different question. So the question says you have to calculate the number of moles of bromine and the number of moles of iodine formed. Now, when you pass chlorine gas through potassium bromide and potassium iodide, initially the chlorine gas would react with potassium iodide because iodide is a more powerful reducing agent than bromide. Now, the potassium iodide is a more powerful reducing agent than potassium bromide. So when you pass chlorine gas through a solution of potassium bromide and a solution of potassium iodide, initially all the iodide would react because iodide is a more powerful reducing agent, because here in this reaction iodide is a reducing agent, right? So let us first write the equation of chlorine with iodide, because chlorine will initially react with iodide first, producing chloride and producing iodine. Now the number of moles of iodide is 0.33 mole, right? And when chlorine reacts with bromide, this reaction produces chloride and bromine, and the mole used is also 0.33. The number of moles of chlorine used, the total number of chlorine used is 0.250 moles, right? So initially what we do is we find the number of moles of chlorine that reacted with I minus. Now the mole ratio is 2:1, right? So this would be equals to half into 0.330. Half into 0.330 is 0.165. This is the number of moles of chlorine that actually reacted with I minus, right? So therefore, moles of I2 formed, see the mole ratio of chlorine is to I2 is 1:1. So the moles of iodine formed will be 0.165, would be the same, right? Okay. Now, this much of chlorine has reacted with I minus, because initially chlorine will react with I minus. So this much of chlorine has already reacted. So the remaining chlorine will react with the bromide, right? So the moles of chlorine reacted with Br minus moles of chlorine that reacted with Br minus will be equals to the initial moles of chlorine was 0.250. The amount reacted was 0.165. If you subtract, this comes out to be 0.085, right? Okay. So therefore, moles of bromine formed will be equal to 0.085. So these are the two answers. So the moles of iodine formed, because they asked to find the number of moles of iodine formed, number of moles of bromine and the number of moles of iodine formed, assuming that all the chlorine has reacted, because initially the chlorine reacts with iodine. So from the number of moles of iodide, we find the number of moles of chlorine that reacted, and from the number of moles of chlorine that reacted, we find the number of moles of iodine formed. And from the remaining amount of chlorine, reacts with the bromide. So the initial moles of chlorine subtracting the moles of chlorine that already reacted, we get the number of moles of chlorine that reacts with the bromide. And from this mole, we find the number of moles of bromine formed. So these are the two answers to this question. Then we move to question number 19. 19b2 is the question. Iodine and iodine monochloride are solids of standard temperature and pressure. Calculate the enthalpy change of formation of iodine monochloride using a Hess's law cycle and the data shown. Okay, you are to draw a Hess's cycle here, right? So the equation is I2 gas plus Cl2 gas gives you 2ICl gas. You have to find the enthalpy change of the formation of iodine monochloride. Okay. If you want to find the enthalpy change of formation of iodine monochloride, then iodine should be a solid, because it says enthalpy change of formation of iodine monochloride. So at room temperature, because it says these are solids at standard temperature and pressure, if you have to find this the enthalpy change of iodine monochloride, del HF, so this equation represents the formation enthalpy. Because when you are writing equation for formation enthalpy, all the substances must be in their standard state, right? So it says iodine and iodine monochlorides are solids of standard temperature. It means both iodine and iodine monochloride are solids under standard conditions. So this must be a solid. So I2 solid reacting with Cl2 gas gives you ICl solid. This equation represents the formation enthalpy of iodine monochloride. Now we have to find del HF. We have to calculate del HF using the Hess's cycle. Now one Hess's cycle here. What we can do is we can combine these equations, right? Yeah. Okay. So we can write this equation here. This equation. You can write this equation here. I2 gas reacts with chlorine gas, produces 2 moles of ICl gas. No, sorry, it was a gas. Yeah, ICl gas, right? And the enthalpy change for this reaction is minus 30. And here, if you look, we can move from I2 solid to I2 gas. This equation, I2 solid to I2 gas. And the enthalpy change is plus 62. From Cl2 gas to Cl2 gas, there is no change. So you can give an arrow and write 0 here. And you may not give an arrow at all, because the enthalpy change is 0 here. From Cl2 to Cl2 is 0, right? From ICl solid to ICl gas, right? So we have an equation where ICl gas turns into ICl solid. So you can give an arrow from the ICl gas to the ICl solid, ICl gas to ICl solid. And the enthalpy change is minus 102 kilojoules per mole. Now using this as a cycle, you can easily calculate del HF, right? So the equation would be, these arrows all are in the same direction. So del HF will be equals to plus 62 plus minus 30 plus minus 102, because all the three arrows, they point to the same direction. So you add all of them, and that would be equal to formation enthalpy, that will be equal to the formation enthalpy, right? And I think I think it's fine. So if you calculate the final answer would be plus 62 minus 30 minus 102. So the answer would be minus 70. Now there is one catch here. What we have calculated here is not formation enthalpy, because this can't be formation enthalpy. You can write del H here, but not formation enthalpy, because the formation enthalpy is for the formation of 1 mole. So this was the formation for 2 moles, right? Because since there were 2 moles, I wrote 2 moles here, but you can't write this as formation enthalpy, because formation enthalpy is only for 1 mole, not for 2 moles, right? It's only for 1 mole. Formation enthalpy is for 1 mole, so you can't write del H F here. You have to write del H. So del H is found to be minus 70. Now this del H value is for the formation of 2 moles of ICL. You need to find the formation enthalpy for 1 mole of ICL. So del HF will be equals to del H divided by 2, because the value del H is for 2 moles of iodine monochloride, and the formation enthalpy is for 1 mole of iodine monochloride. So this would be minus 70 divided by 2. So your final answer will be minus 35 kilojoules per mole. Alright. Then we move on to the next question. It says question number 20. It says why magnesium carbonate decomposes at a lower temperature than strontium carbonate. Because magnesium ion is smaller. And since the magnesium ion is smaller, it has a greater or a higher charge density. And that is why the magnesium ion would polarize the carbonate ion more. So the covalent bonds, or the covalent bonds which are the CO bonds within the carbonate ion, they become weaker, much weaker than the CO bonds in strontium carbonate. Alright, I hope you can write this answer, because we have explained this answer many times before. I think even in the last year's question, or maybe the previous year's question, last year or the previous year, I think in October 25 or May 25, we had a similar question. Question number B says you are to devise an experiment to find the relative atomic mass of Q using this equipment. What equipment do you have? You are provided with a test tube, a Bunsen burner, and a balance. So what you do is, what we can do here, we will take a measured mass of QCO3. We'll heat it in a test tube using a Bunsen burner. Before burning, we'll take the mass of QCO3 along with the test tube, and then heat it in a test tube using the Bunsen burner, and we'll keep on heating it until the mass becomes constant. When the mass becomes constant, or you can write we heat it until a constant mass is obtained, or you can simply write heat to constant mass. It all means the same thing. You keep on heating it until the mass becomes constant. Basically, you heat it, then you heat for some time, then you take the mass of the test tube. If the mass decreases, you heat again, then you take the mass again. If the mass decreases, you heat again, right? You keep on heating until you get a constant mass. When you get a constant mass, you don't need to heat anymore. Okay. So after heating, you subtract. See, you subtract the final mass from the initial mass. See, when we heat QCO3, it produces QO and carbon dioxide, right? So if you subtract the final mass from the initial mass, basically you get the mass of carbon dioxide. And from the mass of carbon dioxide, you can find the moles of carbon dioxide by dividing the mass of carbon dioxide by 44. If you divide the mass of carbon dioxide by 44, you get the moles of carbon dioxide. Now the mole ratio of CO2 and QCO3 is 1:1. So the moles of carbon dioxide equals the moles of QCO3. Now you know the moles of QCO3, and initially you have taken a measured mass of QCO3. So you know the mass of QCO3, and you also know the moles of QCO3. So the mass of QCO3, if you divide the mass of QCO3 divided by the moles of QCO3, you get the molar mass of QCO3. When you get the molar mass of QCO3, from the molar mass you can find the relative atomic mass of Q by subtracting the molar mass of CO3. So I have taken a screenshot from the marking scheme because it's a very long answer, so it would be save our time. So we weigh the test tube. Sorry, my bad. So we weigh the test tube, then we heat the solid. Then we heat the solid in the test tube until there is no change in mass. We calculate the moles of carbon dioxide, right? We calculate the moles of carbon dioxide from the loss in mass, because the mass lost is equal to the mass of carbon dioxide, because carbon dioxide gas was lost, and that is why there is a decrease in mass. Calculate the molar mass of QCO3, because we know the mass and we know the moles of QCO3, we can find the molar mass, and from the molar mass you subtract the mass of CO3, which is 60, you get the relative atomic mass of Q, and from the relative atomic mass of Q you can determine the identity of Q, right? Okay, we move to the next question. It says question number C, identity of Q in a sample of the carbonate QCO3 can also be found using a titration method. 1 gram sample of QCO3 was reacted with 50 cm cube 0.4 mole per dm hydrochloric acid. When all the carbonate had reacted, the excess hydrochloric acid was titrated with 0.2 mole per dm sodium hydroxide solution. The titer was 32.25 cubic centimeters. So this is a very similar question. In the last 2 sessions we had a similar question, so you should expect a question tomorrow, a similar question tomorrow on these. So what we do is we find the moles of sodium hydroxide. Moles of sodium hydroxide will be 0.2 multiplied by 32.25 into 10 to the power minus 3. Concentration multiplied by volume. This would be equals to 0.2 into 32.25 divided by 1000 gives you 0.00645. This is the moles of sodium hydroxide. This is equals to moles of hydrochloric acid that remained. This is the moles of hydrochloric acid that remained, right? This is equal to the moles of hydrochloric acid that remained, because the moles of hydrochloric acid that remained was titrated with sodium hydroxide, right? So then we calculate the moles of hydrochloric acid added. The moles of hydrochloric acid added was, the concentration was 0.400, the volume was 50 into 10 to the power minus 3, concentration into volume, so 0.4 into 50 divided by 1000 gives you 0.02. Then we find the moles of we find the moles of HCl that actually reacted with QCO3 will be equal to added minus remaining. Added minus remaining will give you the moles of HCl that reacted. The moles added is 0.02 minus remaining is 0.00645. So if you subtract minus 0.00645, so it comes out to be 0.01355. So that is the moles of HCl that reacted with QCO3. Now we find, therefore, the moles of QCO3. This would be equal to 0.1355 multiplied by half. Because when QCO3 reacts with hydrochloric acid, the mole ratio is 1:2. When QCO3 reacts with hydrochloric acid, the mole ratio will be 1:2. So whatever is the moles of HCl that reacted, the moles of QCO3 will be half that of the HCl reacted. So 0.1355 divided by 2 will give you 0.006775. And from here you can find the molar mass. Molar mass of QCO3, which would be mass divided by number of moles, 1 divided by 0.006775. Mass was 1 gram, yeah. So the molar mass is found to be 1 divided by 0.006775 equals to 148 grams per mole. Now you find the relative atomic mass of Q by subtracting 60 from 148, because 60 is the molar mass of the carbonate ion of CO3 2 minus. So 148 minus 60, 148 minus 60 is 88. So you have to identify the element Q. Now 88 is the relative atomic mass. So 88 is closest to strontium. So Q must be strontium. It has to be a group 2 element which has a relative atomic mass of 88 or very close to 88. Alright. Oh, then we move to question number 21A. It says the skeletal, you have to draw the skeletal formula of Z-hex-3-NL. Said Z, it should be a Z isomer, right? Hex 3, it means there would be, should be a Z isomer. So the high priority group should be on the same side. Hex 3, right? So the double bond will be on carbon number 3. And high priority group should be on the same side. So I have put all the high priority groups on the same side. This is hex 3, N1 all. There's 1, 2, 3, 4, 5 carbon atoms. Then we have the 6th carbon atom. And the 6th carbon atom will have a double bonded oxygen. So you give a double bonded oxygen because it's an aldehyde. Because it says in L, right? 1, 2, 3. So there's double bond on carbon number 3. Then it says E hex 2NL. So let us copy this, paste it here. It's an E isomer. So this high priority group should be on the other side. Should not be on the same side. It should be on the other side. It should be like this. High priority group should be on the other side. When the high priority groups are on the same side, that's a Z isomer. When the high priority groups are on the opposite side, then it's an E isomer. Why these two are structural isomers but not geometric isomers? These are not geometric isomers because they have different structures. They have different structures because they have different positions of the carbon-carbon double bond, right? Okay, they are isomers. These two are isomers because they have the same molecular formula. So one mark that you get is to write isomers because they have the same molecular formula. right? They have the same molecular formula. But they have carbon-carbon double bond. In different positions, so are not geometric, so they are not geometric isomers. All right. Then we move to question number C1. It says the presence of a double bond can be identified by the addition of bromine water. Skeletal formula of a possible product of this reaction. It says functional group in hex 3N1 all can be identified. It says hex 3N1 all, which was hex, this is hex 3N1 all, right? This is hex 3N1 all. Let us draw hex 3N1 all first. Hex 3N1 all looks like this. There's a double bond here. And I think there's OH. This is X3N1 all, right? So you are reacting with bromine water. If you react with bromine water, so you put a bromine here and one OH here, that would be the answer. It's an addition reaction. With bromine water, the major product is actually the one with one bromine and one OH. So this would be our answer. All right. Then question number D, it says describe in outline the technique for converting an alcohol such as hex 3N1 into an aldehyde, such as hex 3-enal. Oh, you want to convert a primary alcohol into an aldehyde. In order to convert a primary alcohol into an aldehyde, you are supposed to heat with potassium dichromate 6 in dilute sulfuric acid. Basically, you need acidified potassium dichromate 6, but you should write the name of the acid, that this alcohol is reacted or is heated with dilute sulfuric acid and potassium dichromate 6, and the mixture has to be distilled, right? Now, why do you need to distill the mixture? You need to distill the mixture so that it doesn't undergo further oxidation and form a carboxylic acid, right? So it needs to be distilled. So that is how you write the answer. You would write that the alcohol is heated with you should write that the alcohol is heated with dilute sulfuric acid and potassium dichromate 6, and the mixture is distilled, or the product mixture is distilled as soon as it forms, to prevent the aldehyde undergoing further oxidation. And you can also draw a diagram for simple distillation, that is also okay. Saturated non-cyclic alcohols with 6 carbon atoms can be classified as one of the 3 types. Explain these 3 types of alcohols, giving an example of each. Okay, example of each. There are 3 types of alcohols here, right? 1 degree. In the answer, you should mention 1 degree, 2 degree, and 3 degree. And we explain what's 1 degree, 2 degree, and 3 degree alcohol. In 1 degree, the carbon-bearing OH has 2 hydrogen. In case of 2 degree, the carbon-bearing OH has only 1 hydrogen. In case of 3 degree, the carbon-bearing OH has no hydrogen. So you explain, how to classify 1 degree, 2 degree, and 3 degree. Which one of them is 1 degree, which one of them is 2 degree, and which one of them is 3 degree. You must classify them. If you don't classify, you don't get marks. All right. Then you must give example, because you have to give an example of each, of a 1 degree, 2 degree, and 3 degree, from saturated non-cyclic alcohols with 6 carbon atoms. With 6 carbon atoms, you can give so many examples, right? 6 carbon atoms, you can draw the structure and give the example. 6 carbon atom, a molecule with 6 carbon atoms, CH3, CH2, CH2, CH2. It's a non-cyclic alcohol, right? CH2 saturated. 1, 2, 3, 4, 5, 6 carbon atoms, which is 1 degree. You mentioned that it's 1 degree. Then you draw a secondary one. the carbon bearing OH must have only one hydrogen. So that's 2 degree. 1, 2, 3, 4, 5, 6. And then you draw 1, 3 degree. The carbon bearing OH does not have any hydrogen. So that's 2 degree, that's 3 degree. So your answer should include the explanation of 1 degree on how to classify which is 1 degree, which is 2 degree, and which is 3 degree. You explain them. And then you give examples from organic compounds having 6 carbon atoms. One of them is 1 degree, the other is 2 degree, other is 3 degree. All right. Then question number F4. Why 2 alkenes formed in the reaction in F2? Now, when I checked this question, I think there was a mistake in this question. This should be F3, because F2 doesn't form any alkene. Only F3 in F3 alkene is formed. It says using potassium hydroxide under different conditions produces alkene. So alkene is formed in F3 and not F2, right? Alkene is formed in F3 and not F2. So in F3, alkene is formed because hydrogen can be lost from the either side. Because in F3, elimination occurs, right? So let me draw the structure for you. Oh, the structure is already here. So 2 different alkenes can form. If the question was why does it form 2 different alkenes, 2 alkenes? If you look at the structure here, now in F3, what happens? Elimination occurs. So now when elimination occurs, this chlorine can get eliminated with this hydrogen. If chlorine gets eliminated with this hydrogen, the double bond, the position of the double bond would be here, right? The position of the double bond would be here on carbon number 2. All right. Now, if the chlorine gets eliminated with this hydrogen, the position of the double bond would be here on carbon number 1. So it can form either 1 in or 2 in, depending on the position of the hydrogen getting eliminated. All right. I hope you got the explanation. If you have any questions, you can write in the comments. Okay, thank you for today.